Good morning. You all know now that today's topic is 5+2 cycloadditions. It is a very uncommon kind of cycloadditions though, and we have been talking about 3+2, 4+2 etc., but often this is not covered in textbooks, 5+3 cycloaddition reactions, but this is one of the very useful cycloaddition reactions in heterocyclic chemistry. And as you can see from the name that this sort of reactions would provide you with a 7-member ring, 5+2, so 7-member ring systems, and normally with 1 heteroatoms. So that means somewhat restricted but useful. That means it can provide a 7-member ring with 1 heteroatoms, either oxygen or nitrogen. Occasionally it has been applied to sulfur compounds. Okay. Before we talk about this 5+2 cycloaddition reactions, what we will do, we will discuss about a new kind of aromatic ions. First, what I will tell you, number 1, that what is a pyrrhelium ion. I do not know whether you have heard of this name before, pyrrhelium ion. Then next we talk about their reactivity. Then we talk about it is a special kind of pyrrhelium ion which is known as oxidopyrrhelium ion. And again we talk about their reactions, and subsequently we will talk about the preparations of 3 oxidopyrrhelium ions. Pyrrhelium ion, I should say pyrrhelium ion precursors, which is actually, or rather which are produced from a very well known reaction. Many of you probably do not know, this is known as Alkenes reaction. It is a very useful but and very simple reaction. So one can do it in undergraduate labs. Okay. And before we talk about all these things, let us just very briefly look at what are the aromatic ions. How many kinds of aromatic ions are you familiar with? When I say aromatic ions, the commonest one is no, commonest one, because you will be using commonest one is Cp minus. Probably next commonest one is probably tropylium ion. So there are not many actually. Then one other ion could be iron. So like cyclopentadiene an ion, tropylium cation. And so what are the other possible aromatic anions or cations could be? Cyclooctadiene is not very okay. Cyclooctadiene dianions are not very common, but there are other kinds also. For example, many of you know cyclopropenium ion, cyclopropenium cation, that is also pretty useful. Okay, many reactions are observed or rather done with the cyclopropenium ions. But what about heteroaromatic ions? Have you heard of any heteroaromatic ions? Not many. So actually not many. Actually one of the commonest ones is basically pyrrhelium ion. Mind it, pyrrhelium ion, and which is nothing but it comes from pyrrhine ring system, and a double bond here, and also obviously oxygen is trivalent. So it has to be plus, and then the corresponding counter ion. So this is actually pyrrhelium ion. You have to mind it, this the spelling, you have to be very careful about the spelling. because P y R y. If you write R I, then you are gone, means you will be directed to different others perineum. Okay. So, you will not get this what in internet, and this is a very well known, well characterized, and they are considered to be aromatic by virtue of this electron that is 6 electrons in a ring system, all the pi electrons are fired. And then how do I know these are aromatic? Because they are stable to be isolated. That means many of these salts can be isolated, recrystallized, and then they can be stored in ambient conditions. But then there are limitations. For example, this sort of molecules or salts would not react with any electrophilic reagents. Traditionally, when I say aromatic means it is at what are the two items we talk, or the two words we talk about, they are stable and they can undergo electrophilic substitution reactions. But in this case these salts are stable, but they do not undergo any kind of electrophilic substitution reactions. Instead, they undergo a nucleophilic substitution reaction. Nucleophilic, for example, if you just take put ammonia here, you will get simple pyridine. Okay. That means let us say the exact example is like this one. If you have a methyl beryllium salt, put ammonia, then of course you get the methyl pyridine, 4-methyl pyridine. And the reason why I gave you this example, simply because 4-methyl pyridines are difficult to make. How do you make? There are not many ways. You cannot just take pyridine and do electrophilic substitution reactions to get you a 4-methyl pyridine. Is there any alternative method for 4-methyl pyridine? Standard aromatic chemistry would not provide you the 4-methyl pyridine. But in this case, you can see here the salts can be done. We will see the salts are very easy to make. I will give you more examples. Let us say one of the so this is one of the let us say characteristically, just how do you characterize them? One of them, of course, the NMR. How do you know what are the chemical shifts of these hydrogens? These hydrogens, the chemical shift should be guess, that means 2 hydrogen, 2 or 6. So, delta H of 2 hydrogen circle the hydrogen is of approximately 9.2 ppm, 9.2 ppm. So, that signifies that this hydrogen could be aromatic. Not only that, this delta carbon, again this C2, when I talk about the C2 or C6 is approximately 169 ppm. So, from there you can characterize them, and how to make them? Very easy. The salts could be, I mean, unbelievably very simple starting metal. For example, you take this one, tertiary butanol, okay, and then acetic anhydride, and the catalyst here is tetrafluoroboric acid. So, what do you expect? This is a very simple reaction though. What is expected out from this reaction? Normally, primary and secondary alcohol would react with acetic anhydride very easily, either in the presence of acid or in the presence of base like pyridine. But if you have a tertiary ones, they are sluggish to react with acetic anhydride. And you have hexafluoroboric acid, sorry, tetrafluoroboric acid. This is a pretty strong acid. So, under these circumstances, what you will see that it loses water. So, you produce isobutylene, and then acetic anhydride is an electrophile. So, acetyl cation. So, acetyl cation will react in that means it is a 2 equivalents of these. So, eventually what we will get a sort of a say pentadione kind of thing with this one, pentadiene and this one. Just do it, this is basically electrophilic substitution electrophilic reactions of alkenes. That means the basic reaction would be looking like this. If you have isobutylene and then you have acetyl cation. So, what you will get? You will get a reactions of this kind, and then once again you can have one more, right. So, sorry. So, acetyl here, this carbon, then go to this one, next one. So, what you will get? You will get this one, right. And then again if you have acetyl cation here, so this would react, it will then isomerization and eventually you get to this compound. So, it is a very easy preparation. Now, this one does not stay in this form, in the presence of this tetrafluoroboric acid. So, eventually it will form the corresponding salt, the pyrrolium salt and this methyl and the methyl, that means very easy to make, And so, and then what I said that electrophilic substitution reactions are not permitted with this sort of compounds, but if you have right nucleophile, you can get with amines you can get the pyridine derivative. So, I will give you one more example, very classic example. This is taken from 1994 JCS, many of you know, Perkin transaction 1, page number 1035. In this case, what you will see, it is just not a simple pyrrolium ion. So, you have an oxypyrrolium ion. In this case, it is a it's a 2 pyrrone. You start from 2 pyrrone now. That means, you have a oxo group here, and then substituent here and there, then you have a methoxy group here. Now, if you use a very strong methylating agent, in this case methyl fluorosulfonic acid. Methyl fluorosulfonic acid is one of the very strong methylating agent. So, what do you expect now? It is basically a source of hard methyl ion, methyl plus. So, equivalent to this is methyl plus, just like methyl iodide, methyl sulfate and this, and occasionally we will also use methyl triplet also. So, what do you expect here? Because of this aromaticity gain due to the participation of the oxygen lone pair. So, you will get the pyrrolium salts and oxygen here and these, then this methyl here, oxygen plus and the corresponding anion here. So, once again you get the pyrrolium salt. What is the reaction expected out of these? If you now react with a phosphonate salt, phosphonate is basically is a ester containing phosphonate, the CH2, then phosphorus and oxygen, in this case is a methyl phosphonate. Then these. So, what do you expect? It forms the anion here, right, carbon ion. So, carbon ion and that would, that means this carbon ion would attack this carbonyl here, it is a symmetrical one, it does not matter, the methyl here, it does not matter which carbon. So, eventually what you will get? You will get this methyl here, carbonyl, and then here what you will have CH, right, then this ester group, and then you have this phosphonate So, basically a simple nucleophilic substitution reaction, nucleophilic substitution reaction. What next? What next? Ring closure. Again the ring closure means basically you have a carbonyl, inbuilt carbonyl, and you have a phosphonate. So, you will get the Wittig-Horner reactions, Wittig-Horner reaction. So, eventually what you will get? You will get this double bond here, that means CH3, and in this is in this case this is OMe here, by the way, this is OMe, and now you have this ethyl ester. Okay. So, what is the net result? So, it is a basically it is a we are now talking about a very reactive class of intermediates. Normally there are many kinds of intermediates, okay, but in this case the reactive intermediate is the pyrrhelium ion. Okay. In the reaction with heteroatoms we could produce the pyridine derivatives. Now, if you use a carbon ion you can get to the benzene derivative. So, that means starting from the heterocyclic compound you are making an aromatic compound. Okay. And similar to this, that means in this case you mind it has 2 pyrrole. Now, this now the situation is if you have a 3 pyrrole system, that means what I am talking about is talking about something like this. So, basically with respect to oxygen the keto is the 3 position. So, 3 pyrrole. Now, and if you have a cation of this kind, for example, in this case, so what we can see that you will have a nice resonating structure and okay, if I minus here. So, this would give you again a pyrrhelium salt with deuterionic characters, deuterionic structures, but the cyclic structure represents a aromatic structure, and this sort of intermediates are known as 3-oxidopyrrhelium ion, and they are very useful intermediates, There are 2 reasons. They can be made very easily from very well known reactions called Akhmatovic reaction, we will talk about towards the end of the class, and it undergoes, unlike non-oxidopyrrhelium ion, a class of cycloaddition reactions with a variety of reactants, and in this case we will be calling those reactants Dipolarphile. We will not call the like traditional Diels-Alder reactions what we say diene and dienophile. In this case we will talk about Dipolarphile. So, that means these 3-oxidopyrrhelium ions would serve as a dipole, and if you see the resonating structure on your left, it is a basically 1-3 kind of dipole, 1, 2, 3 dipole. But since it belongs to a 5-membered cycle, 5-membered system, 1, 2, 3, 4, 5, neglecting the oxygen. So, this is called 5 system. So, there are debates whether it should be called a 3 component, 3 atom component or 5 atom component, and normally people have accepted that this should be called as 5 atom components. Okay. And as I said before, unlike the simple pyrrhelium ions or even the 2 pyrrhelium ions, these oxidopyrrhelium ions will work in the cycloaddition reactions. Then the dipolarphile could be of many kinds. Okay. So, the initial, let us say if you have large excess of kind of ethylene, what do you expect? You expect a reaction basically what do you expect a reactions here, so that as if this electron goes to this and then the negative charge neutralizes this. Although we are writing in the ionic form, but they are truly cycloaddition reactions. So, truly cycloaddition reactions. And how do you remember? is okay. That means the molecule should be 3 oxidopyrrolium ions. Secondly, it could be a simple alkenes or styrene, indene, all kinds of alkenes, and we will give you more examples. We will give examples, and so what you get here? You get here is a what 3, 2, 1 bicyclooctenone systems, but with an oxygen bridge here. The reaction is very facile. I will just give you one example that would tell you how good the reactions are. Let us say, but if you have a pyrone, 3 pyrone here and the double bond, then of course you need a leaving group, right. In this case, if it is acetoxypyrone, 1, 2, 3, 4, 5, 6 acetoxypyrones, and treat these with triethylamine at room temperature. Triethylamine at the room temperature. So, room temperature, then you treat with ethyl vinyl ether. Okay. So, what do you expect from these reactions, from this series of reactions? What do you expect? See, this is triethylamine at room temperature, that means such a very first reaction. It forms the carbanion here, it forms this oxido part, here, and oxygen here. Then this oxygen lone pair of course expels the acetate ion. So, you get truly there is a 3 oxidopyrrolium ions in situ. This is not. Then of course, then this ethylene part, that is dipolarphile, and the ethoxy could be on this, on your left hand side, on the right hand side, right. So, which one is expected? This is unpredictable, but you get one. That's why I have been telling you that the reaction is unique in the sense it is just not like these simple Diels-Alder reactions, diene and dinophiles, that one would be electron rich, other would be electron poor, and vice versa. But in this case it is very unpredictable, but in this particular example it gives only one, and many of us know that when you have a ethoxy ion here, this olefin becomes electron rich, but in most cases what you will see that the second carbon, that means with respect to the oxygen, right, 1, 2, 3, this is the numbering. So, this one is the second carbon. So, this is electron rich, it should attack the electron poor carbon of the dipolarphile, but in this case what you have, it basically goes to the other way. It could be, there are two reasons. It could be the repulsions of these two oxygen, on the same side, but it is not just typical the cycloaddition reactions. Okay. So, then this one would go, and eventually what you will get, this compounds very similar. One can coolly write this way. So, that means you will get a alpha beta unsaturated kind of a system here, and this, and then this double bond here, and this ethoxy group here. Okay. Pardon me? There is no region, absolutely there is no region, it is found. Okay. I mean, I can speculate that this, if it is oriented in the other fashion, this oxygen minus would be closer to oxygen. So, there could be some repulsion, the repulsions of the two, between the two oxygens, that could be one of the reasons, because nobody says anything about that. Okay. But what does it tell you? This example has a peculiar, it is a lesson. What is the lesson? That these 3 oxidopyrrolium ion can undergo cycloaddition with electron rich olefin. Okay. Let us look at one more example. I mean this under the same conditions or rather very similar condition I should say, if you take this acetoxypyrone and simply heat it in the presence of a little excess of course, in the excess of acrolein, okay. So what do you expect? Again a very simple reaction, the material is simple, easily make, and the acrolein is commercially available, no reagent, just simply heat it. And this has been proven, in the NMR tube actually this can be made, and this oxidopyrrhelium ion, and this has been tested before. Fine. Now let us look at the reaction. So if you have this kind of beryllium cation, so now you can quickly see, right, what can be done. This easier to see if you have a polarized double bond, well polarized double bond. That means this is plus and this is minus, right, we all know, right, because of these polarizations of the double bond. And in the case of beryllium ion, of course the electron rich carbon is second carbon, 1 2 3 second carbon. That means this goes here and then this is reacting with the other carbon. That means the bonds are being formed across the ring oxygen, that is how you can remember, okay. And when I write, actually first I write this way, that means this, okay, this and the new bond that are being formed this way. So dotted lines you can say they are the new bonds, and across this double bond olefin here, and then you have aldehyde, okay. And one can argue here why this aldehyde is beta here. Absolutely, well, there are attempts to explain this, that why it should be XO and endo, all these things, but they are unpredictable. If you just substitute this acrolein by acrylonitrile, that means in the place of aldehyde with cyano you get a mixture of the compounds. So these are a little unpredictable, but as far as the regiochemistry is concerned, these reactions proceed in the manner the way we have shown. And suppose you do not add aldehyde or any other dienophile or any other dipolarphiles, then what do you expect? You get a kind of reactions basically without the presence of any kind of dipolarphile, this intermediate dimerizes. I will not give you the structure, but just remember they just undergo dimerization reactions. What else? This again the same molecule, same kind of molecules here. What are the other possible reactions? If you have reactions, let us say with something like these alkenes here, it is a substituted alkenes. That means so long we have seen the examples with alpha beta unsaturated aldehyde, okay. Then we have seen this vinyl ether. In this case it is not a vinyl ether, it is simply an alkene. Now you have two different kinds of these, two different kinds of the double bonds. Now okay, in the previous example what I said, that electron rich double bond also can participate, electron deficient double bond. Now you have a reaction, you have a dipolarphile which has both kinds of these double bonds. Now how to decide? Well, since I know the result, I know the answer, it is easier to say, but again in this case only the one that is sort of less hindered, I would say, less hindered. I think this is how it is easier to remember. The one that the plain one, unsubstituted part of this alkene system would participate in the reaction. Eventually it will give you product this kind. So once again the lesson is, what is the lesson? the lesson is that this sort of reactions would provide again a bridged alkenes with alene, and so likewise there are other kinds of, let us say what else you can think of, okay. So, simple alkenes, okay, styrene, as I said, styrene can be reacting dipolariphile, then electron deficient double bond, electron rich double bond. Now you have an alene systems. What else can you think of? Acetylene, alkynes. Alkynes also have been shown, but they are sluggish to react. That means they are not very popular. What else? Reactive double bonds. Where do you get the reactive double bonds? Reactive double bonds could be like non-bonded ion systems. If you have a strained double bond, for example, many of you have studied Pauson-Kant reaction. How many of you studied Pauson-Kant reaction? Pauson-Kant reaction is a very popular reaction. Very good. Okay, reagents. Dicobalt, octacarbonyl, alkyne and an olefin. So, you get that is basically very popular reaction to make cyclopentadiene, okay. But there is a limitation, that is what you have to know. What is the limitation? The limitation is that this reaction works well with reactive double bond. If you take simple alkene, olefin, butene, propene, it will not react. So, you have to have a reactive double bond. So, where do you get the reactive double bond? How do you get a reactive double bond? If you make it a strained system, for example, if you take a non-bonded ion system, okay. So, similarly in this case also, if you have a reactive double bond, like say how else can you make reactive double bond? One of the kinds of the reactive double bonds are the bonds embedded in non-bonded ion system, okay. What else? Where else? Where else? Where do you get this reactive double bond? Well, that may not be alkene. Okay, let us say benzene, for example. It's a kind of a double bond. It undergoes 2+2 cycloaddition, other 4+2 cycloadditions. So, there is reactive double bond. Where else? Where else? I said strained system. So, if you have a cyclopropene system of this kind, it is very easy to make. Again, it is easy to make. Then this will undergo this kind of the cycloaddition reaction, 5+2 cycloaddition reaction, 5+2 cycloaddition. Okay. Now, let us look at one more example. Now, it is not a simple pyrone. We have this acetoxy, 6-acetoxy pyrone, and now you have a substituent here with a double bond, inbuilt double bond. You see there is a difference now. What is the difference? Now, the double bond is within the substrate, and what is the reaction conditions? The reaction conditions could be room temperature, a base, or simply heating, just 150 degree centigrade. And in acetonitrile, of course, as boiling point of acetonitrile is 180, sorry, only 80 degree, but if you are to react at 150 degree, so you have to put them in a chill tube and do the reaction. So, what do you get? So, that means under thermal conditions this will form again this oxido ones, and how do you orient them? So, it is a 2, right, one 2, the third one is carrying, and then you have a double bond, right. So, this should be the orientation, and again the bond would form across the oxygen. So, that means this one would form here and this one would form here. So, essentially what you will get? You will get a 7 membered ring. Quickly to easy to remember, you have to have alpha beta unsaturated system. When it ends, so you will have an oxygen part here, that and then the substituent goes with 2 carbon, the third one is carrying a methyl group here, and by virtue of steric effect this this hydrogen would be this beta here, and what you get is basically once again it is a 7 membered ring system, 7 membered ring system. So, what is the lesson? Basically this is an example how to construct a bicyclic molecule now, bicyclic molecule, okay. And so truly speaking it is a tricyclic molecule, because you have oxygen bridge here, so tricyclic molecule. And what else you will learn from this example? That is basically we have to take the message. First of all, you have to do a little bit of the practice of these reactions, then you have to get the lesson of this reaction. What is the lesson? Intramolecular reactions. That means and the double bond does not have to be very activated, does not okay. It is a simple alkene also would undergo a reactions, okay. Now, this reaction is so useful. I will just give you a better example where this reaction can be extended to the synthesis of a natural product. In the one the next substrate will a little more complex now, little more complex, look alike. Once again it is a pyrone system. Now, the substituents are a little different. This is O acetate here and this TBS, all of us know, tributyl dimethyl tributyl tertiary butyl, not tributyl, tertiary butyl dimethyl silyl group, and then you have a defined stereochemistry here at this alpha position here, then a substituent with methyl group, then acetate here, and then acetate here, and then you have a homoallylic system part, homoallylic part. Okay. So, you have a nice complex substrate. Now, if you just treat this with DBU, diazobicycloaddition, and solvent is acetonitrile. So, just a strong base in the place of triethylamine. So, what do you get? Like the previous example, what you will get is just once again the loss of acetate and the formation of this hydrogen formation of carbon ion leads to this oxido system, and then bring this double bond adjacent to the oxygen and just attach it across this double bond. That means the positions of 2 6 positions of the pyrone system, and it would look like once again it will look like a 7 membered ring alpha beta unsaturated system. See, this is how and then next carbons are linked through this oxygen here, and this the rest of the 2 carbons comes from the double bond part, and so double bond part, then you have that means basically 1 2 3 4 5 6. So, what you will see, you will have a 6 membered ring, 6 membered ring and then this acetate, and what you get here again because of these because of these substituents you get the single diastereomers, single diastereomers. And why do you make this? Because this can be converted into a 5 membered, 7 membered, then a 6 membered, and then a 3 membered, all kinds of, you do not have to write, but just to get a feeling that this can be converted into a very complex molecule of this kind, and then with fixed stereochemistry, or defined stereochemistry I should say, defined stereochemistry, and so many functional groups here and there. Then you have a double bond here, then this OH and I mean many things. And what is it? It is a very famous molecule actually. It is a famous molecule, is not is known as 4-ball, 4-ball, and it is a basically lead compound for anti-cancer and anti-HIV activities. Okay. So, this molecule has been of interest for many years, and this has been prepared by Paul Wender, which is a well known chemist, and but the methodology relied upon this one. Okay. So, briefly what we have talked about so far, that pyrrhelium ions, then if you have the acidoxy group as a substituent, you can just simply heat to get the pyrrhelium ions, or you can use triethylamine or DBU to produce this. And then once the intermediate is produced in C2, without isolations they can be submitted to the cycloaddition reactions with a variety of these alkenes, and these new bonds are formed across the double bond, across this oxygen. So, that is the lesson. What next? Next is, if you just have more carbonyl at the 4 positions, that means 4 pyrone system, 4 pyrone system, then a kind of molecule of this kind, for example 4 pyrone, and if you treat this with let us say methyl triplet, what is expected? Yes, methyl triplet, what is so methyl triplet is basically equivalent of methyl sulphate, methyl iodide, that means methyl cation here. So, what you expect here, once again you will get a you will get a pyrrhelium ion. What is the driving force? Driving force is the aromaticity. So, and this sort of molecule is now is well known, So, and what you get is this corresponding pyrrhelium ion. Okay. Now, this just switch over to a similar molecule. Now, what you will see, that means this sort of molecule can undergo reactions to form pyrrhelium ion. Now, the same reactions similar or rather similar kind, 3 hydroxypyrone now, 3 hydroxypyrone, which is equivalent to the 3 oxido pyrrhelium ions. Now, you have an additional carbonyl group here, Okay. And in the presence of, let us say again this methyl triplet, what you can expect? You can expect a pyrrhelium ion now, right, and what else? Because negative charge. So, this charge is neutralized. So, you get this corresponding deuterion or beta-ene. So, essentially what it is? It is this 3 oxidopyrrhelium ion. You have it is a substituted 3 oxidopyrrhelium ion. That means the methoxy, there is a additional methoxy group at the 4 positions, Now, do this reaction. So, let us say with let us say acrylonitrile, once again the reaction would proceed at the 2 position, and the double bond would now move to react with the other positions of the pyrrhelium ion. So, what you will get? You will get so you will get again a 5-membered ring, 7-membered ring with the oxygen bridge here and the cyano group here. So, this is essentially it's a new kind of reactions now. This is a new kind of reactions, but only that it incorporates an additional methoxy group here, and these reactions are has been very useful in the sense you do not have to have this methoxy group pre-formed methoxy group here. You can do in situ. For example, there is an example here. If you take 4 pyrone system and you have an inbuilt double bond. Of course, inbuilt double bond means you may think about an intermolecular reactions. So, it is what you see here, this is called just simply heat it. So, what do you expect? I mean, there is a reaction normally in polymer chemistry people talk about this group transfer. What does it mean? It means one of the groups would transfer from one place to the other, and probably many of you know in this case what is expected here, this oxygen lone pair would react with the intermolecularly to the silicon, very similar to a reaction known as Brook reaction, right. Brook rearrangement. What is it? Migration from no, from carbon to oxygen, from carbon to oxygen. Okay. Here it is actually oxygen to oxygen, oxygen to oxygen. Am I right? Okay. So, then once this occurs, so what you get is again a oxido. So, oxido and beryllium ion, that is it, and the rest of the thing is as usual, and you have sulfur, then you have allylic system here, allylic system here, and by virtue of the geometry this these two positions would react at this end, and the double bond now moves to the beryllium ion. So, if you rewrite it will be again a semi-membered ring with double bond here with this is TBS, and then there is a now sulfur heterocycles and oxygens are linked again sorry, in this case it is beta here, and so with this geometry you can get to this compound. Okay. So, then actually this has been also converted to an advanced intermediate of a natural products if you use Rani nickel. So, what you will get sulfur will be removed. So, what will be you will be getting Rani nickel is very selective, right, very selective, very selective. You have double bond here or TBS, and what else. So, with Rani nickel what you will see, double bond is not reduced, carbonyl is not reduced, sulfur would be knocked out, and so only thing that means now you are converting this into the to methylation. Okay. So, I think there are many examples, but then why that means what you see here these 5+2 cycloaddition reactions are very versatile reactions. You can have, that means 2 ways to get these beryllium salts. One of these ways to just loss of acetates, and second is basically the group transfer. Group transfer is normally done on the 4-oxo pyrone systems, okay, and often the silicon is used as the group transfer. And very recently there are examples where this sort of reactions also has been developed into an asymmetric synthesis. If you have right kind of catalyst, I will just give you probably this reference. You may look at this reference here. This is a Jack's publications by Jacobson, and 144 this is the reference. What you will see this reaction also can provide enantiomerically pure compounds. Example is something like this. You will have this double bonded compound here, this pyrone system, then you have here this alene system here, it gives you the 5+2 cycloaddition reaction, 5+2 cycloaddition reaction, intramolecular cycloaddition reaction, and but the catalyst is of course the chiral catalyst. What is the chiral catalyst? Many of you know Jacobsen's is now famous for a special kind of the chiral catalyst. What is that chiral catalyst? Based on thiourea. So, now he has actually used 2 kinds of thioureas now. So, and he has named them is a cooperative catalyst. So, 2 different, so that means 2 thiourea catalysts have been used together to produce the corresponding product in enantiomerically pure form. With the alene systems, the enantiomeric excess have been very close to 95%. Just you can look at this reference. Okay. And lastly, I will just very briefly tell you why this reaction is so famous 5+2 or very popular, because I told you that I will tell you about a reaction called Akma-To-Ich reaction, right. WICZ is a Polish person reaction. What is it? If you just start with a simple furfuryl alcohol and treat this with bromine and methanol. I think all of you know this reaction, right. What do you get? This is a BSC reaction. So, furan ring does not get destroyed, it remains as it is. So, aromaticity is destroyed, double bond. So, okay. So, you have a double bond up here, that means if of course, when I do not write anything, that means you are using 1 equivalent of bromine, right. 1 equivalent of bromine, so 2 bromines adds across this oxygen again, that is substituted by methanol. So, methanol here and the other substituents remains as it is. Okay. But if you treat with 1% sulfuric acid, that means very dilute sulfuric acid, what you will see, this is actually what happens, this is equivalent to a 1,4 dicarbonyl compound, right. So, these central carbons are equivalent to basically acetals and ketals. When they hydrolyze, they form the corresponding ketones, but because of the stability it recyclizes. That means this alcohol cyclizes to this one, and eventually what you get is very easy to get these pyrone systems, that means the precursors of the pyrrhelium ions. So, that is the reason why there are 2 reasons, the materials, the precursor or the starting materials are easy to make, number 1. Number 2, they can be made to react with the olefin or alkynes, varieties of alkene substrates under mild conditions. Mild conditions means just a DBU or triethylamine or simply heating. Heating means less than 200 degree. So, most of the reactions are carried out in less than 200 degree centigrade. Okay. And there are other examples, maybe I mean this Akma-To-Ich reaction is actually is very useful in the sense that you can have all kinds of the furan substituted compounds, okay, here and there, and also the chiral centers here and there, and because the only under very mild conditions you are getting to the corresponding pyrones. Okay. In this case, if you look at this bromine and methanol, which is equivalent to what is that? It is an oxidation reaction. So, can you substitute, for example, for ring opening of this furan to corresponding pyrone, what else can you think of? What other reagent can you think of in the place of? No, I said bromine and methanol, just to substitute bromine and methanol. Bromine and methanol give you dimethoxy, in presence of acid it hydrolyzes to corresponding ketones. Okay. That can be substituted by simple oxidizing agent, because the whole process is an oxidizing agent, oxidation. Okay. you can use metachloroperbenzoic acid for example. Metachloroperbenzoic acid you can use. You can use surplus epoxidizing oxidation reagent. What is that? No. No, the one that is used for epoxidation. Vanadium? No. When I ask all these things, you have to remember all these things. See, first thing you have to remember the stoichiometric oxidant. Which one is the stoichiometric oxidant in epoxidation of surplus epoxidation? No, surplus epoxidation. Tertiary butyl hydroperoxide. Then you talk about the catalyst. What is that? Vanadium diacetyl acetonate. So, this is the reagent. So, that means in this case you can use metachloroperbenzoic acid or this. And see in the second reaction here you are actually hydrolyzing it, available starting material or rather reagent. N-bromosuccinamide plus water. What is it? Anybody knows what it is? Is equivalent to hypobromous acid. So, that basically bromonium electrophile adds one across, then other portion OH, then the bromine adjusts. These Akmatoi reactions are very useful because of this availability of so many kinds of the reagents. Okay. And so, I think this is all about this today's one. And next time probably we will have little more problems in next class, and few more reactions based on 2 plus 2 plus 2 cycloaddition reactions in heterocyclic chemistry. If you have examples, bring them. Okay, we will discuss. Okay, what is that? Next class we will talk about 2 plus 2 plus 2 in heterocyclic chemistry.